Good afternoon. Happy you made it here. Thank you for joining this presentation of XJet nanoparticle jetting. This is my first time at Ceramitec and I'm very excited to be here. My name is Dror Danai and in the next 20-25 minutes I invite you to join me on a journey exploring the power of powderless in ceramic additive manufacturing. How many people here are familiar with AM or additive manufacturing at all? Don't be shy. How many people learn about additive manufacturing today for the first time? Okay, that never makes the whole team. Okay, the other just prefer German, but my German is very limited. When additive manufacturing was introduced 30 years ago, the focus and the original products and technologies were targeted at plastic, mainly polymers and other plastic additive manufacturing. And over this period of more than 30 years, and I see some faces that are more than 30 years in the industry, over these years, the uses of these parts, mainly for prototyping, expanded to the point that in this world, a prototype of any major product that you have at this second in your pocket, like your cell phone, is first made with additive manufacturing or rapid prototyping or 3D printing in order to create a new product. 15 years later, metal also started to recognize the value of additive manufacturing, and at least in Germany, all the car makers and even tier 1 and tier 2 suppliers to the car industry will use metal additive manufacturing. Ceramic, relatively, is a new user of additive manufacturing. But at the same time, being the smallest in adoption, it's the fastest in growth, in a position that it at least doubles the number of installations, the number of applications, the number of users every year. And it is predicted that that will continue. And we at XJet, our booth is just behind me now, the booth next door, we at XJet with the new technology presented here at Ceramitec for the very first time. This technology, we hope, will enable more applications and more use of additive manufacturing also in ceramic applications. Many articles were written about additive manufacturing over the last 30 years. But for those of you who hear about it for the first time, I tried to concisely put it in two statements, and they're in front of you. You use additive manufacturing for one of the following two reasons. You use it either when you want to make a short run. Whenever the run length is in millions or hundreds of thousands, you will find other ways that are more effective and typically cheaper for the producer of the part. So run length makes a big difference. And the more people ask me this morning, which applications are best for additive manufacturing or for XJet, the best is when the run length is smaller, all the way down to a run length of 1. Imagine that you are driving a very expensive car and you want your signature on the driving wheel, on a ceramic beautiful part in the middle. That can be done very easily with additive manufacturing. Go figure a mass production way to do it. Okay, so mass customization is one driver of additive manufacturing. So it's always about the run length. Aviation is another example where additive manufacturing was well accepted because most of the planes in the world, or all the planes in the world, are made in a series of 100, 200s. I don't think Boeing had many planes that reach 500 planes a year. So whenever the run length is short, additive manufacturing, the creation of the parts in an additive way, is used. The other parameter is complexity. take a small part that has very simple features. There would be a way to create this part in existing technology, whether it's machining, molding, or others. There are very, very good processes that you use today very successfully to create these parts. But if you have a short run length or a very complex geometry, that's where additive manufacturing comes to help you. A little bit about who we are. We are not experts in ceramics, not yet. We are here to learn and educate ourselves about this industry. But we are expert in inkjet, and that's what we are doing as a team, actually in a few different companies, but the same team, the same founder, and the CEO of the company are going together since the early 90s with the introduction of very high quality 2D wide format for billboard advertisement. Later on with the creation of XJet in the beginning, the late 20th century for making polymer prototypes. And now with XJet and nanoparticle jetting that can create parts of ceramic as well as metal. We are based in a science park not far from Tel Aviv in Israel. A big investment over the last 10 years, mainly in R&D, mainly in creating new basic XJet patents, was put together, and as we get to the commercialization, we are over 100 people now. What you see here is an example of complexity. This part that you can see 10 meters behind me in our booth, this part is a drill, but for those of you who look closer, you see 2,400 conformal cooling channels here, all leading to a central channel. Each one of them is only slightly over 110 microns in diameter. Okay? And the XJet technology and additive manufacturing is probably the first that enabled the creation of such an example. We have developed new levels of innovation with the introduction of nanoparticle jetting. We like to put them in 3 different sections, and each one of these sections will lead to some new opportunities and new possibilities. On the left, you have the issue of stochastic nanoparticles. Stochastic or random means that we use powder that doesn't need uniform, doesn't require, like most of the additive manufacturing systems, doesn't require our particles to be the same size. Furthermore, they are not even in the same shape. That saves us a lot in the creation of this material, but also it has some benefits when it comes to the mechanical properties and the structure of the part, and I will explain that. The second area of innovation is the fact that we use cartridges, just like in home inkjet, a little bit bigger, and if we have one, we'll show you in a few minutes. And we use 2 different materials, and that's unique to the industry. Most of the parts that are made in additive manufacturing are made of a single material. Since we are using inkjet technology and we are jetting the material itself, we are not a binder jetter, we are jetting the material itself. We jet what we want and where we want on an empty tray. Doing that simultaneously allows us to get to even more creative design. And because we use nanoparticles and we use very, very thin layers, we can create very, very nice geometries. Let's start with the first one. the stochastic and the very small particles enable us to get to almost 100% density. Particularly, our parts, after they are sintered, have no porosity. Okay, no porosity at all. Another thing is that, which is in additive manufacturing, we are adding a layer after layer after layer to create a part. This is the secret or the source of advantage of additive manufacturing. But it comes with a price. Typically, when you look and you start to look at the microscope or try to do some structural or physical, mechanical properties check, you will see a difference between the X, Y that are similar to the Z that is different. Since we are building a green part, and since there's no stress between the layers, we do not stick them in any way, the parts come in the same structure and the same mechanical properties on X, Y, and Z. The other advantage that we get in comparison, let's say, for ceramic injection molding and other additive manufacturing systems that already exist, we do not use this vast amount of binder. Now, being able, we're using high temperatures, but being able not to use a large amount of binder, we also see very low shrinkage in the sintering process. This is just an illustration to show the ability to create. When you're working with same structure, same size, and same shape, you may get some voids. When you go into active direct jetting of the material and using different size, not in this illustration, but it's also different geometry of the particles, you get what we call natural packing, and that leads to lack of porosity. If we look a little closer at this animation, you may see again that this gives a structure that doesn't fit a perfect nature, and on the right-hand side you can see the XJet result. This is a picture from SEM, and you can see 1 micron is, this is a micron. You can see how it looks under the microscope. By the way, at the end of my presentation, we brought a microscope here, so you can take our parts and play with it yourself and see the shape, and you can see the fine details. So from the part properties, that was the red part of my presentation, we move to the green part. Because we are using, this is a support cartridge, by the way, because we are using a different material for support, the support will fit in all the undercuts, the channels, everything that is needed to make, as I said before, very complex geometry. But it comes with another advantage. The support structure that may be in many AM systems, may be a hassle, disappears. So you can take any geometry, and because you use another material that has completely different mechanical, but furthermore, different physical properties, it's a totally different material, we use these different properties to dissolve it in a water-based solution. So that's taking one part that people that are more familiar with AM, the part that people don't like to talk about, the part of removing the support. So the support is planned automatically. Let's say that you have this part, automatically you can print by pressing the print button, like you print an Excel spreadsheet or a Word document. Okay, and that's a big difference for our industry. Also, once it's done, support removal takes a few minutes, but all these minutes are made in what we call a jacuzzi that take away the support structures away. And it's a very clean, you don't hear the machine is running now live behind me, and you can't hear it. And also it can work in an office environment because we don't deal with powders at all. Basically the operator of the machine, all he needs to know is how to put it in the machine, and we can show you later how it's being done. He doesn't need to wear any powder protection. So just for the illustration, on the left, these are metal parts, but it's same, maybe true for also ceramics. The support structure in the traditional additive manufacturing systems is made of the same material, which means that you may need a Dremel or any other tool, mechanical tool, to separate the support from what you build. At XJet, we're using a completely different material, so it's easy to remove. Also, as you can see, the cartridge is on the right. That's easy to put in. The way that we print, in a short video in a few minutes we'll go into more details. The way that we print is that we add liquid to the nanoparticles of the ceramic. Because as I said earlier, we know very little about ceramics, but we know a lot about inkjet. Inkjet needs liquid to be jetted and a certain load. So we create a very high load relatively to what has been achieved before, and we suspend the particles. The particles here are the build, and this is the support particles that are jetted. So we talk about properties, mechanical properties. We talked about the operation. I would like to finish with the geometry. The fact that we can use any geometry because of the use of two different materials, there's no limit. Because we use very thin layers, we can get fine details and very smooth surface, or in short, very near net shape to the part that you want to make. In this is a metal part, but again, you can see very tall, thin walls. We can go down to a few hundred microns, or even 100 microns on certain features. And if you look closely on the right-hand side, you can see that by having layers that are less than 10 microns, we create a surface finish that requires very little or no post-process. So before we summarize it, the value is in mechanical properties, in much easier operation, and in ability to reach near net shape. And hopefully this video will explain that.
Previously on XJet.
XJet nanoparticle jetting. Welcome to a new era in metal additive manufacturing.
Now it's time to demonstrate how XJet leverages the same nanoparticle jetting, or NPJ technology, for ceramic 3D printing, using our new Carmel line of AM systems. Unlike existing approaches, XJet's NPJ is a highly versatile and scalable inkjet-based technology. NPJ uniquely empowers the manufacturing of high-quality ceramic parts of virtually any design with superfine details, all in a simple and safe process. So, how does it work? Ceramic materials, packaged within convenient cartridges, are easily and safely loaded by hand into the XJet Carmel AM system. With no need for a powder or liquid vat, the Carmel system uses only the materials required. Suspended within our unique liquid formula, nano-sized particles are jetted from thousands of inkjet nozzles. These nanoparticles, of various sizes and shapes, are randomly distributed to allow for natural packing and high density. Liquid droplets containing either ceramic model or support materials are simultaneously deposited onto the build tray in an ultra-fine layer. The ceramic part builds up as the tray descends with each pass of the inkjet print heads. After printing, the support component, made of a soluble material, is easily disintegrated, allowing for fast and clean support removal. The non-UV sensitive materials utilized by NPJ technology enable simple single-step sintering. Our versatile NPJ technology empowers the rapid production of ceramic parts with superfine details, unprecedented safety and simplicity, and unrestricted geometries. XJet nanoparticle jetting technology and the Carmel line of AM systems, redefining ceramic additive manufacturing.
And now, after 10 years of many people, a lot of work, we're coming out of the labs and start to go into partnerships We welcome you once again at the end of this presentation to come and talk to us. We installed the first few machines, actually the first ever machine coming out of Israel is here in Germany, near to Magdeburg. And a few more machines are installed already, and now we're starting to ship a few more. And we want people that are ready to embrace new technology and to help us to develop the applications and to fine-tune the use and maybe even the character of our technology. So this is happening today. Next month, our first American customer will hold the first ever open house. So if you happen to go to an NBA game of LeBron James, it's about 20 minutes away from where he was born in Youngstown, Ohio. In June, to be able to meet the needs of the market and ability to scale up our business, we're taking another step. We already contracted a world-scale leading manufacturing company to do the final assembly of our systems. This should enable us to increase our production significantly. And in July, another major day for us is the inauguration of the additive manufacturing center. The manager of the center should be around here, and if she's not, Liat is there, so she will be happy to tell you more about this center. This is a center of more than 2,000 square meters with 10 unattended Carmel additive manufacturing systems, and we hope to open it before the end of July. And finally, in August, we're moving to the new offices. I don't know if you can see it, but it's behind this beautiful team of people somewhere there to enable us to continue our growth as the company moves into commercialization. This is part of the XJet team and the real power behind this new technology. I'm very happy also to share with you that big part of the team leaders of the company are here today and throughout the show, so you are very welcome to come and visit them. And with that, I would like to thank you for attending this presentation. Do you have a couple of minutes? I guess I finished 7 minutes before schedule, so any questions? Was completely unclear or too clear?
Thank you for your presentation.
Thank you.
What kind of ceramic materials, technical ceramics can you use?
Excellent, excellent question. We have experienced and was very successful to do tungsten carbide. Actually, we really printed cutting tool that were inserted into a machining operation. And the first product that goes to market now is, it's all technical ceramics. The first product is zirconia, ZRO2. We are also working in the lab, and maybe it's the first time we announce it. We are working in the lab. It will take some time until we go into field testing or even internal testing, but the second material that we're working on is alumina. Okay? Now, it's a very good question. To create ink takes time. Getting the powder is easy. Relatively, there are very good suppliers of ceramics powder. Excellent. Maybe some of them are sitting around us now. But but this is only the first phase. Once you created the powder that is inserted into the ink, you need additional materials, tens of different materials, to create something that will flow in the right speed and in a smooth way, but at the same time will have a nice load. Okay, because we don't want to be, you can do it very easily and put 1% weight load. But in order to get something that is effective and efficient, you want to go to very high load. So that takes time. Obviously, over time, we hope to be able to create many more materials and faster, but today this is what we are offering.
And
Yes, please. Where are you from?
France.
Okay.
What is the load, maximum load you can reach?
The maximum load from theoretical perspective, probably in the range of high 60s, low 70s. Practically what we see today, what we experience today is in the range of 50%. Obviously this is a weight load, meaning the weight of the particles, in this case the ZrO2, 6 grams per cubic centimeter approximately. This means that in volume it's a lot less. So this allows us the beautiful flow without hurting the inkjet heads and still get a very high efficiency and very high speed. Thank you. Yes, please. The width. I don't know if my colleagues will allow me. They worked very hard to find that. But maybe later we can discuss it on a one-on-one. But the range for the zirconia is sub 100 micron and more than 10 microns. In silver, which is not covered in my presentation today, we went even below because we grew the silver by ourselves. But here we are in the range of, let's say, 10 to 100. 10 to 100 nano, sorry if I was, 10 to 100 nanometers. And you are from? France as well. Bonjour, mes amis. Oui. Yes, please.
What about the printing speed? Can you say something how long it will take to build up something which is 5 centimeters?
Yes. Basically, speed or the productivity, I think that's even in our case more important, because we cover, it's a raster system, and they say raster is faster. What does it mean? We cover the entire tray whenever we go with the build block, okay, or the printed block, which means that you can put a single part or 100 parts and it will take the same time. So the time it takes to build a layer, let's say in 1 hour today with the zirconia we are approximately going a 1.5 millimeter. Today, obviously there will be faster systems in the future, but today the system makes, so a part of 1 centimeter high, if I calculate correctly, and you are welcome to comment, should take, and it doesn't matter if it's 1 part or 100 parts. For example, in the case of dental applications, we printed a tray of 489 crowns in one print. Okay, so let's say, and for that, let's say you need 1 centimeter, so that will take you approximately 6 hours. So you could say 1 crown 6 hours, or 400 and 500 crowns per 1 hour. Am I clear? The math is clear. Okay. Oh, sorry, yes. The question was, do we plan to create a system that jet at the same time multiple materials? This is the essence of our future. We believe that the future, I'm not talking about this year or not even next year, but in the longer term, hopefully in the next Ceramitec, we'll make some announcements about multiple materials. Because once, and this is the beauty of jetting directly different materials, because all the systems that I'm familiar with are typically using the same material at all times. Even the binder jetting approach takes, for metal printing, has a powder bed and then the add binder. In material jetting, we jet today actually 2 materials already. Because, and there's a beautiful virtual reality, I know there may be a little bit of a line, but it's worth waiting, that explain that and really take you inside the machine, allowing you to see how it's being done. So we already print, on the Carmel we have 24 printed, jetting more than 200 million droplets per second. Half of the heads, 12 heads, are being used for the build material itself, and half for the support to create the geometries I mentioned earlier. Now imagine that you take some to jet material A, some to jet material B, and the rest will be the support structure, which is always needed. All of a sudden, with small decrease of speed, you get on the same machine an ability to print A, B, and combinations of material A and material B. I'll take one more question. You allow me? Okay. So I'll just sum up. We have nanoparticle jetting, a new way to create ceramic parts that gives you unlimited geometry, gives you a smooth and simple operation, and gives you very high density and very natural packing. To see that, we are here behind me is the whole XJet team. There are a few experiences that you may want to choose from. There is a virtual reality screen that shows you what happens inside the machine. There's an augmented reality screen, and there's a touch screen that shows you different pictures. So this is right behind me. If you go further inside the booth, there's one more interesting station where you can see the machine on one end, and next to it you can see a table with a microscope, and you can bring your own part or our parts and look under the microscope and see how little or how thin the details are. Thank you very much.